Black holes are among the most mysterious cosmic objects, much studied but not fully understood. These objects aren't really holes. They're huge concentrations of matter packed into very tiny spaces. A black hole is so dense that gravity just beneath its surface, the event horizon, is strong enough that nothing, not even light, can escape. The event horizon isn't a surface like Earth's or even the Sun's. It's a boundary that contains all the matter that makes up the black hole. Most supermassive black holes are found in the centers of galaxies. They sit in the gravitational driving seat as hundreds of billions of stars in the surrounding systems happily orbit them, just like the planets orbit the sun at the center of our solar system. Black holes don't emit or reflect light, making them effectively invisible to telescopes. Scientists primarily detect and study them based on how they affect their surroundings. Black holes can be surrounded by rings of gas and dust called accretion disks that emit light across many wavelengths, including X-rays. A supermassive black hole's intense gravity can cause stars to orbit around it in a particular way. Astronomers track the orbits of several stars near the center of the Milky Way to prove it houses a supermassive black hole, a discovery that won the 2020 Nobel Prize. When very massive objects accelerate through space, they create ripples in the fabric of space-time called gravitational waves. Scientists can detect some of these by the ripples effect on detectors. Massive objects like black holes can bend and distort light from more distant objects. This effect, called gravitational lensing, can be used to find isolated black holes that are otherwise invisible. Welcome to the world of space. Today we're talking about black holes, with a special focus on one called TON 618. Now imagine this. Take all the stars in our galaxy, the Milky Way, and squish them together to make a black hole. Even after doing that, TON 618 would still be much bigger, billions of times more massive. How did it get so huge? Let's find out. TON 618, the most massive black hole we know of, still has an entire galaxy of stars happily orbiting it and not getting sucked in. It's a common misconception that black holes act like vacuum cleaners, when in reality, it's incredibly difficult to grow a black hole. For a start, you have to get the material close enough for it to be affected by the black hole's gravity. And when you consider how dense black holes are, due to all that matter being squashed into such a tiny space, and how vast the universe really is, you start to realize just how difficult that can be. If matter does stray too close, however, it will get pulled in by the black hole's gravity, and that gravity increases dramatically the closer you get. Think of it like walking up a hill, but the hill becomes steeper with every step you take. It's brutal. This monster, appropriately named TON 618, weighs roughly 40 billion solar masses. TON 618 has a radius of over 1,000 astronomical units, AU, which means that if the black hole was placed in the center of the solar system, by the time you reached Pluto, you would be less than 5% of the way from the center of the black hole to its edge. TON 618 sits about 18.2 billion light-years away from Earth. In the night sky, it sits on the border between the constellations Canis Venatici and Coma Berenices. Astronomers first spotted it in a 1957 survey from the Tonantzintla Observatory in Mexico, but didn't realize what it was. They first thought it was a faint blue star, but observations a decade later revealed that the astronomers had glimpsed intense radiation from the material falling into the giant black hole. TON 618 powers a quasar, one of the brightest objects in the entire universe with the illuminating power of 140 trillion suns. Quasars draw light from the gravitational energy of the central black hole. The material around the black hole falls in, and as it does so, it compresses and heats up, releasing enormous amounts of radiation. While individual events like the most powerful supernovas can briefly outshine quasars, they only last a few weeks. In contrast, quasars can shine for millions of years. As a quasar, TON 618 is believed to be the active galactic nucleus at the center of a galaxy, the engine of which is a supermassive black hole feeding on intensely hot gas and matter in an accretion disk. The light originating from the quasar is estimated to be 10.8 billion years old. Due to the brilliance of the central quasar, the surrounding galaxy is outshone by it, and hence is not visible from Earth. With an absolute magnitude of 37, it shines with a luminosity of 4×1040 watts, or as brilliantly as 140 trillion times that of the Sun, making it one of the brightest objects in the known universe. Like other quasars, TON 618 has a spectrum containing emission lines from cooler gas much further out than the accretion disk, In the broadline region. The size of the broadline region can be calculated from the brightness of the quasar radiation that is lighting it up. Schimmer and co-authors used both NV and CIV emission lines in order to calculate the widths of the HB spectral line of at least 29 quasars, including TON 618, as a direct measurement of their accretion rates and hence the mass of the central black hole. The emission lines in the spectrum of TON 618 have been found to be unusually wide, indicating that the gas is traveling very fast. The full-width half maxima of TON 618 has been the largest of the 29 quasars, with hints of 10,500 kilometers per s speeds of infalling material by a direct measure of the HB line, an indication of a very strong gravitational force. From this measure, the mass of the central black hole of TON 618 is at least 66 billion solar masses. This is considered one of the highest masses ever recorded for such an object, higher than the mass of all stars in the Milky Way galaxy combined, which is 64 billion solar masses and 15,300 times more massive than Sagittarius A*, the Milky Way's central black hole. With such a high mass, TON 618 may fall into a proposed new classification of ultramassive black holes. A black hole of this mass has a Schwarzschild radius of 1,300 AU, about 390 billion kilometers in diameter, which is more than 40 times the distance from Neptune to the Sun. However, quasars are so far away that they only appear as faint spots of visible light in even the most powerful telescopes, and astronomers first detected them by their powerful radio emissions. Quasars are actually supermassive black holes that are feeding. Supermassive black holes become enormous through a combination of merging with other black holes and by constantly feeding on surrounding material. This feeding rate is what sets the limit on the size of a black hole. These cosmic vacuum cleaners can only consume so much material in a given amount of time. As material falls in, it heats up and releases radiation, creating a quasar. But that radiation heats the material itself, preventing it from quickly falling into the black hole. This self-regulation prevents black holes from growing too quickly. Astronomers can estimate the maximum mass of a black hole by taking that feeding rate and multiplying it by the known age of the universe, giving an estimated maximum mass of around 50 billion solar masses. However, that is only an estimate. There may be other, more exotic ways to create large black holes, such as from the direct collapse of large clumps of dark matter in the early universe. So it's still possible that there are even more massive black holes out there. Not every collision will result in such a drastic energy exchange. On average, there'll be an equaling out of the energy. Eventually, one particle will have enough collisions and be unlucky enough to lose energy in everyone, bringing it ever closer to the black hole. It's only when the particle has a collision in the region, known as the innermost stable circular orbit, ESCO, that it will finally cross the event horizon to become a part of the black hole. The ESCO doesn't exist in Newton's theory of gravity, which we all learn at school. Newton's theory says that all perfectly circular orbits, no matter their distance, are very stable. That means if an object on a circular orbit is unsettled slightly, it'll remain largely on the same orbital path. For instance, if something was somehow orbiting near the Sun in a perfect circle and was nudged by another object, its orbit might become more oval, but it would continue orbiting the Sun. That's not the case in Einstein's theory of relativity, however. As you get closer to an object like a black hole, there comes a point where, if you nudge an object on a circular orbit, or say one particle were to collide with another, that object couldn't correct its path and would end up spiraling in towards the black hole. That point is the ISCO. It lies around 3 times further out than the event horizon and, usually, marks the inner edge of the orbiting disk of matter. This process of particles colliding, exchanging energy, and falling over the event horizon accretion takes a very long time. We're talking millions of years just to get a black hole to a size where it can snack on a passing gas cloud that drifts too close. How much matter can fall into a black hole? Complicating matters even further is the fact that there's also a limit to how much matter a black hole can accrete in a given time. The universe effectively puts a black hole on a diet if it becomes too gluttonous. This happens because the disk of matter orbiting a black hole is moving and colliding at such an incredible speed that it starts to heat up due to friction. It's heated to such an extreme temperature that it glows like metal in a forge. The good news about this glow is that it allows us to spot black holes and measure how massive they are. The light can, and does, outshine entire galaxies, making them look like single pinpricks of light. These pinpricks were originally dubbed quasars, a portmanteau of quasi-stellar because they look like stars but aren't stars. It was only after the Hubble Space Telescope launched in the early 1990s that astronomers could make out the galaxy of stars that went with each quasar, and their true role in growing supermassive black holes was revealed. The bad news for black holes is that the glow is so intense that it exerts a pressure outwards, radiation pressure, that prevents any more matter from falling in. If there's too much material in the disk, the radiation pressure increases and pushes material away from the black hole. There's a fine balance between the size of the black hole and the quantity of matter in its disk, and when a certain threshold is reached, depending on how massive the black hole is, the rate at which it can accrete material is capped. What makes TON 618 so exceptional is the sheer amount of physics standing in the way of a black hole growing to that size. But while we've known for a long time that radiation pressure places a limit on how fast a black hole can grow, known as the Eddington limit after astronomer Sir Arthur Eddington, what we didn't know until recently was whether there's a limit to how massive a black hole can become. As far as we know, there isn't. Theoretically, you could keep on merging black holes to your heart's content, gradually increasing the overall size, as if you were making a giant snowball. But there is a limit to how big black holes can grow via accretion. In 2015, Prof. Andrew King at the University of Leicester published a paper that pointed out a quirk of gravity around black holes. The quirk allowed him to estimate the maximum mass a black hole could achieve via accretion, 50 billion solar masses. But it could be 270 billion solar masses if the black hole was spinning fast in the same direction as its galaxy. At the root of this quirk is the position of the ISO, which, like the event horizon, is related to how massive the black hole is. As the black hole's mass increases, the ISO gets pushed further out. The problem for a growing black hole is when the ISO is pushed beyond what's known as the self-gravitational radius. The distance that the self-gravitational radius sits around a black hole is another factor that's related to the mass of the black hole, but it also depends on the object that's approaching it. The self-gravitational radius marks the point at which the pull of gravity holding the approaching object together, self-gravity, is stronger than the pull from the black hole. The self-gravitational radius is why we're all here. It's why we're able to have entire galaxies surrounding supermassive black holes. Beyond this radius, gas in a galaxy is attracted more to itself than to the black hole lying at its center. If this wasn't the case, gas would never collapse to form stars, and instead, our atoms would just be part of one giant disk of material orbiting a supermassive black hole. It was King who pointed out that when a black hole reaches 50 billion solar masses, the ISO gets pushed beyond the self-gravitational radius. What that means is that no matter how many collisions they have, any particles in the disk of material orbiting the black hole will never lose enough energy to reduce their orbit to a point that allows them to reach the ISO and spiral into the black hole. Instead, the pull of gravity from all the other particles in the disk will always be stronger than the pull from the black hole. That's if there even is a disk of material around the black hole, because any matter that isn't on a direct, bullseye trajectory with the singularity as it approaches won't get pulled into a disk. Instead, it will loop around the black hole, spaghettified, but otherwise unscathed. This lack of a disk means that we also won't be able to spot such a black hole, as there'll be no luminous matter around it lighting up like a Christmas tree. This is why TON 618 is so interesting to astronomers. With an ultra-massive black hole of 66 billion solar masses, it lies above King's estimate of the maximum limit, 50 billion solar masses, for a non-spinning black hole. Most black holes are spinning, which increases the mass they can reach before they push the ISO beyond the self-gravitational radius. But it still means that TON 618 could be nearing its maximum possible mass. It's fascinating to consider the implications of all this. We could be approaching the point in the universe's history in which black holes start reaching their limit. If black holes stop accreting and growing in this way, then they'll also stop glowing. Quasars will begin to wink out as black holes age past their glory days. It's possible that there are other black holes in the universe that have already reached ultramassive proportions. We can try hunting for them, but without the glow of a disk orbiting around them, we'll never spot them. There could even be ultramassive black holes hiding right under our noses. Thanks for watching this video, and see you next time.